Okay, hello everyone. It is 9:02 p.m. Monday, July 14th. I believe that this makes the 50th video, so that's pretty cool. We have done 2/3 of problems, so I mean by our mathematics we should be finished by the 75th day-ish, but I kind of been slowing down as I keep progressing, getting tired and whatnot. So we're probably gonna finish on like the 80th to 90th video, most likely. So we'll see. That leaves me about I would say maximum of 30 more days. So August 14th. So we should definitely be done with this. Hopefully, before like actual interviews start cracking out. Afterwards, I'm gonna move on to grind 75. Work on those. Get comfortable with those. Okay, so today we're going to be doing bit manipulation. Now, I've actually never done bit manipulation, or that's a lie. I have done bit manipulation like once or twice, but it wasn't like I knew it was bit manipulation. It was more like I was working on a problem, I couldn't get past it, and then I had to look at the solution. I saw the solution with bit manipulation, and I just copied the answer and pasted it, and then that was it. So, that was not correct, right? That's not how you solve bit manipulation. But today we're going to try to learn through practice, which is probably not the best way. You should learn first through principle and then practice, but we'll see. Given a non-empty array of integers called nums, every element appears twice except for one. Find that single one. You must implement a solution with a linear one-time complexity. Use only constant space. So okay, I think I've done this one before. I believe this one is you just do n and n and n and n, right? Or sorry, I and I and I and I. So this would basically be like index equals, or we'll say solution equals 0 for element in nums, solution equals solution and element, and then I return solution. Wrong. Maybe I do those one. Two, one, one, two. Ha. Okay, so that's not it. I don't remember the element operations. Is it XOR? Let's look at the hint. It is XOR. Okay, it's the caret. There you go. That one kind of makes sense. XOR basically is true and false is true, false and true is true, false and false is false, right? So everything kind of adds up. This sounds basically like an OR statement, but true and true is false. So XOR is exclusionary OR. Basically that means if there's nothing, then there's nothing. If there's one of them, then there's one of them. If there's two of them, then there's nothing. You kind of can imagine it as a mod, as a mod of basically two for that instance. But I don't know if that makes sense or not. Okay, we're gonna continue on. What I'm not looking forward to actually is this. Math plus bit manipulation? You're joking me, brother. You're freaking joking. Given a positive integer n, write a function that returns the number of set bits in its binary representation, also known as the Hamming weight. Okay, I feel like I have heard of that for sure. Ha! Okay, so the Hemming weight is the number of ones. One, two, three, 4, 5, 6, 7, 8, 9, 10. Interesting. So obviously, like, my naive approach would be making a binary converter, which I did this beforehand, whenever I did this problem a long time ago. I don't remember how I actually did the solution, though. Making, like, a binary converter, and then basically just tracking the ones and whatnot, which is a pretty bad solution. Especially when thinking of like bit operation, we're thinking about like low level, kind of thinking of logic gates. I don't know if you'll heard my cat or not. I don't actually know how to do this one. Wondering if it's like you go in times. One of my naive approaches without doing a binary conversion would be a sort of counter. Ugh, sorry, I'm yawning. So you go with like n times, so 1 you add 1, and then 2 you add 1. Even still, like, that's super archaic. There's a cleaner approach, and we're gonna use a hint, or a couple of them. A couple hints. O of 1. See, exactly. That's what I've been thinking. I was like, this can't be a linear approach. First of all, they give you a huge number off the get-go because they want to see you. I want to see if you can handle it. What? Come on, man. Right, we write 32 times 0 to 31 using index 1. The expression problem than the one I got.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve number of 1 bits. This is actually another Blind 75 problem, and we've been tracking all Blind 75 problems on this spreadsheet. The link to that will be in the description. Today we'll be doing number of 1 bits, one of the last problems remaining that we haven't done. And I also have a YouTube playlist for the Blind 75 solutions. Link to that will also be in the description if you do want to take a look. Okay, so now let's get into it. We are told to write a function that takes in an unsigned integer, which isn't really important for this problem because all we want to do is count the number of 1 bits that it has. So the concept is pretty simple. So when you take a look at this number, we can see it's made up of zeros and ones, and we just want to count how many ones it has. Clearly it has 1, 2, 3, so we can return 3. But how can we actually count the bits? So obviously we need to do a little bit of bit manipulation. I'm going to be showing you 2 different solutions. One of the solutions, the second one, is going to be slightly faster if you're interested in it, and it's pretty difficult to come up with. But the first solution is a little bit more straightforward and is more doable. So like I said, the easiest way is just to count manually bit by bit and then see which one of them are ones and then increment our total and then...
Oh crap. The video might have to end there. I just knocked down my internet adapter and it's no longer connecting. I think that finally broke my internet adapter. My cat knocked it over for months. Actually, years. This thing is years old, so. Wi-Fi extender. Netgear. What is it? Looks like it's knocked out. Well. Alright. I went ahead and placed an order for a new one. Let's see. Oh. I heard something. Hey, we're back. I still got that new one coming because this thing is actually chopped right now. It's like being held together with glue. Okay, we're back on the internet.
And return the total. But let's see how we can actually accomplish that. So how do we know, let's say we want to look at the first bit on the right side. How do we know if it's a 1 or a 0? Well, there's actually two different ways. One way is you can AND it with the integer 1. So since the integer 1 just has a 1...
This is silly. This isn't the right problem.
Hey everyone, today we are going to solve the readable question number of 1 bits.
Again, different problem. Man, this is the type of shit that be pissing me off. I'm like, why did LeetCode change the problem? I can't, like, what am I supposed to do with this? Hold up. Yeah, okay. I'm about to do a login approach. Alright, let's see. Let me do my mental math. So 11 is odd, so that's gonna be 1. And then we're gonna do it 5. 5 is odd, so that's gonna be 1. And then we're gonna 2 is even, so it's gonna be 0. And then 1 is odd, so that's gonna be 1. There you go. Okay. Alright. Well, let's see how this goes. I'm gonna say this is so not right, but I don't even like care anymore. But we'll look up a solution that actually works. But we'll see this for a second. I'm gonna say while n does not equal 0, if n mod 2 is equal to 1, then solution plus equals 1, and n minus 1, and then I'm going to say n divided by equals 2, and then return solution. See if that works. Wrong answer. Really? Oh, yikes. Wait, that shouldn't even be happening. Oh my days. Minus equals. Oh. That was a little slow. Oh, it's because of this big behemoth. Sure. So this is a log in approach. If you know, you know. It's because we're doing dividing by 2 each iteration. Great, that's awesome. Can we do it in a bit way? Let's see it. Let's see it. Man. Okay, thank you. Ah! I like how these are easies. These are confusing my brain. Okay. Oh, right. Python. Python. Oops. N and n minus 1. Is that what n equals? N equals n and n minus 1, and then solution plus equals 1, and then I print n just to test it out. How does this exactly work? Whoa! Okay. What? Someone's gotta explain that for me. The Brian Kernighan. I'm not going to remember this, which sucks, because I feel like I'm going to need that for a future problem. Look at this man. Look at this man. What a dapper individual. He's got that swagger to him.
You worked hard to cross that finish line. Now it's time to celebrate those memories. At Michaels, we help you preserve.
Hi, I Aziz welcome you to Codemaster, and in this edition of number 10 in 32-bit form. So here are the 8 bits that are all unset.
Today we will see about how to count the we got.
Oh, they're already in there. Thing. Well, I guess the and. Interesting. I guess the and treats it as a binary, right? Oh, wait, I think I'm starting to see it. Because if it's a odd number, it gets rid of that first one, and then it just kind of then it stays. It goes back down to the even form. And if it's an even number, then it's getting rid of some 0 or some 1. So no matter what you do, you're always getting rid of some sort of 1. That's a tricky thing to wrap your head around. Interesting algorithm nonetheless. We'll do one more and call it a day. I mean, how much time I got left? 9 minutes. Yeah. Counting bits. Give an integer in. Turn an array answer of length n plus 1 such that for each I is the number of ones, the binary representation. I'm a bit confused on what it's asking here. Give an integer n, return an array called answer of length n plus 1. Such that for each I, 0 less than or equal to I less than or equal to n, answer I is the number of ones in the binary representation of I. Feels almost DP-ish. Is this below DP? It is. Huh. This does feel a bit DP. Should make use of what you have produced already. Okay, dynamic programming. I'm guessing this is DP plus the gentleman Brian. What is this? Kernighan's? Kernighan. Mixture of those two. Mr. Brian Kernighan plus DP. Bit manipulation. Oh. Disconnecting again. No internet. What do you mean no internet? Move in. Okay. DP. A straightforward approach would be to iterate from 0 to n using I, and for each I, it iterates bits to count the number of set bits. This would result in O of n divided by log n. For example, to compute set bits 7, add 1 to the count of set bits 3, which was previously computed by adding 1 to the count of set bits 1. Learn the pattern for numbers less than 4. Add 1 to the count. Ah, it is better. I knew it. That's interesting. I would have never thought about that on my own. See, these are all problems I would have never thought about on my own at all, because I don't know anything about bitwise. I'm like a complete noob on that. 31 seconds left. Come on. Come on. Let's just write this one real quick. We're gonna do a climbing bitwise, or climbing solution. We might not even need the TP thing. Tabulation, brother. I hate it, but we love it. For I in range 1, 2, and in plus. I'm gonna cheat again. It's not gonna give me the correct answer. If I is equal to offset times 2, then offset times equals 2, right? Is that how it works? Okay. Return answer. So this is going to be wrong for the second. For the second one, or aka the third position, which is index up 2. We're not? What? Why is that? Why am I tripping? 2. Oh. I see. That's a cool problem. Tabulation, brother? I feel like I didn't truly understand that, though. Not gonna lie. I actually didn't understand. Not gonna lie. I couldn't just went over my head. you for watching. That was video 50, maybe slightly underwhelming, but you know, bit manipulation. Don't know anything about it, so that's what we're here to do. We're here to learn. I'm probably not learning much right now with the way I'm method I'm using, but you know, we do what we gotta do. Anyways, thank you for watching, and I will see y'all tomorrow.